In the last video, we saw how to recognize strong electrolytes. A strong electrolyte is either a soluble ionic compound or a strong acid. Okay, now you'll be able to tell if something's soluble or not by either looking up solubility and seeing if it's above 0.1 gram per 100 milliliters of water, greater than, or you can look at the guidelines. In your textbook for deciding whether a compound is soluble or not. So you will always be able to look up the solubility. That's the easiest way to decide if something is soluble or not. In many cases, in a test situation, I will tell you whether it's soluble or not. But in the homework, sometimes you will need to decide that for yourself. Now, an ionic compound, you already know, is usually something with a metal and a non-metal. It has recognizable ions inside of it. A strong acid we talked about in the last video, it's one of these six: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, or perchloric acids. If you've got one of those six, it's a strong acid. If you've got an acid, a thing that starts with an H, and it's not on that list, it's a weak acid. So it'll be a weak electrolyte. Now, in this part of the worksheet, it's going to be essential that we can recognize strong electrolytes. We're going to take equations that involve ionic compounds in solution, and we're going to write them a different way. It will be the same equation, but it'll be written in terms of its ions instead of the compounds that are present. Okay? So, let's do an example. Let's suppose I tell you you have hydrochloric acid and you mix it with barium hydroxide. And I tell you, I want you to write an equation, a balanced equation for the reaction between those two things. And I want you to write an equation in terms of the ions that are present. Let's do that. Okay, we had a 5-step procedure in the last video for writing down equations for things. Step 1 was write down the formulas of the reactants. Hydrochloric acid. Okay, if it's got a hydro in front and a nic acid on the end, there's an IDE ending on the ion inside. So the ion inside must be a chloride. So if you put a hydrogen on that makes the acid. So these are the two ions that must be in there. And if we push them together, here's the formula. Okay, let's do the same thing for the barium hydroxide. Barium, if you look at your periodic table, is Ba plus 2. It's in the second column. Hydroxide, you know from your polyatomic ion table. When you put these together, you're going to have to put two of these together with one of those. So there's step 1. We wrote the formulas for the two reactants. The next step is list the ions present. Now, notice that we had to list the ions present in order to work out the formulas, so that step's already been done up here. Third step is swap the ions. So I'm going to make the plus ion from this go after the negative ion here. And what am I going to get? H plus and OH minus should give me HOH, which is really what we call water. And if I make the plus here go after the minus there, if I push these two together, I'm going to need 2 chlorides for every barium. The next step is, are the products soluble? Okay, I'm going to go look up, well, water is a liquid at room temperature, so I don't have to look up whether that's soluble or not. I would probably write that as H2O liquid. Now how about barium chloride? If I look up the solubility, it will be bigger than 0.1 grams per 100 milliliters. And if I look at the solubility guidelines, it says chlorides, bromides, and iodides are soluble, unless you combine them with silver, mercury, or lead. And we don't have silver, mercury, or lead here, so this will be soluble. So that means that I can write that. All right. Now, I'm going to write the balanced equation. Okay, well, what do I have? These are the reactants, so let me write those down. And these are the products. Now, this one is soluble, and this one is soluble too. So there it is. It's not balanced yet though, right? If I take a look at the barium chloride, there are 2 chlorides on this side. So I might think maybe this is a good idea. That'll put 2 Cl's on either side. And now let's look at the H's. I got 2 H's there, and I have 2 H's there, so I should have 4 H's on the other side. But I only have 2, so maybe I want to put a 2 here too. Alright. So now it's balanced. Now, that was what we did a couple of videos ago. We wrote down balanced equations like this. Now what we're going to do in this video is take that and write this molecular equation, that's what this is called, as an ionic equation. And how do I do that? It's pretty easy. Break up all strong electrolytes. So what I have to do is scan across my equation here and look for strong electrolytes, and if I see any, I'm going to break them up. How about this? Is this a strong electrolyte or not? Alright, it's a strong acid. It's in my strong acid list. So that means it's a strong electrolyte. That means that I'm going to break this up into H plus and Cl minus. Now because there's a 2 in front of it, I'm going to put a 2 in front of the H plus and a 2 in front of the Cl minus. So I can write this way. And what I've done is just replaced this with this. Okay, how about this? Is this a strong electrolyte or not? It is a strong electrolyte. Why? It's an ionic compound, metal and nonmetal, and it's soluble. So that means I can break it up. So let's write that as a barium ion plus 2 hydroxide ions. That's what it'll break up into. Now, is this a strong electrolyte or not? Well, it looks like an acid because it starts with an H. but it's not on my strong acid list. So it must be a weak acid. And in fact, water is a very weak acid. And weak acids are not strong electrolytes, so I'm going to have to leave that alone. I'm going to just carry it down the way it is. So whenever you see a weak acid, you just carry it down into the ionic equation the way it is. It's not a strong electrolyte, so you can't break it up. How about this one? Is it a strong electrolyte? Yes, because it's got metal and non-metal, and it's soluble, so it'll break up. Alright, so that's called the ionic equation. Now both of these equations are showing you the same chemical change, the same reaction. They're just written different ways. This one looks a lot more complicated, but there is a way for us to simplify it. Look at things that are the same on both sides, like that barium ion, and like those chloride ions. They are still there after the reaction. And that means that they're not really participating in the reaction. It doesn't change them. They're the same before the reaction as they are after the reaction. If you cancel ions that appear on both sides of the equation, you get what's called a net ionic equation. So the spectator ions, the ones that are the same on both sides, are this, and the barium is the same on both sides. So if I write it like this, that's one form of the net ionic equation. Now if I look at this equation, I can even make it simpler than this, because look, there's a 2 in front of everything, right? I can simplify that equation by dividing both sides of the equation by 2. So it's simpler to write the equation like this. This is the net ionic equation for this reaction. Let's do another one like this. There will definitely be some of these on the Chapter 5 test. How about if we have acetic acid plus sodium bicarbonate? Alright, we have to write down the formula for acetic acid. Now it's got ic acid with no hydro in front. So I know that that's an ion inside there that has an ATE ending. So inside there is an acetate ion. And if I look at my polyatomic ion table, that's the acetate ion. If I make it into an acid by adding H plus ions to it until it is neutralized, there's the formula for the acetic acid. So step 1 is write down the formulas for the 2 reactants. Sodium bicarbonate. Okay, sodium is Na plus, and bicarbonate. Okay, carbonate is CO3 minus 2. And putting a bi on there means you've hooked a hydrogen to it. So it's a hydrogen ion hooked to a carbonate. Now carbonate is CO3 minus 2. So if you hook a H plus to it, it's HCO3 minus. See, all of the stuff that we did in Chapter 4 that had to do with the ions and naming the ions and knowing their charges is really going to matter a lot here with the job that we're doing right now. And if you're lost right now about how I'm getting these ions, you need to go back and study your Chapter 4. Alright, that's a +1 and this is a -1. So those are my reactants. So I have the formulas for my 2 reactants, which was step 1. Step 2 is list the ions. Well, in working those out, I already listed the ions. So I have a list of ions. Step 3, swap the ions. Okay, if I swap them, the positive one here is going to go after the negative one over here. And I'm going to get this, because there's going to be a hydrogen hooked onto that. Now, if I take the positive one here and I hook it onto there, they're going to go together 1 to 1. So I'll get sodium acetate. So these are my two products. Now, do you remember the lab we did where we were forming H2CO3 as a product? This is an unstable product. It's called carbonic acid, remember? And whenever you see this forming as a product, you're going to cross out carbonic acid and rewrite it as this. It's unstable. Whenever you form that in a reaction, it will fall apart. So this is a special rule that is coming into play here, one that we used in that lab that we did a while ago. All right, so the fourth step is going to be to balance the equation. Well, the fourth step is going to be to decide if these things are soluble or not. Well, we already have state symbols on here. We know this is a liquid and this is a gas. How about the other product? What do you think? Well, it's an ionic compound, and it's got sodium in it. If you look at the guidelines in the textbook, you'll see that they say anything that has sodium in it is going to be soluble. So you can put an AQ after this. Okay, so those are the state symbols that we put onto the products. The fifth step is balance the equation. All right, here are our reactants, these two things. Acetic acid plus sodium bicarbonate gives me, here are our products. And sodium acetate. Now, if they were asking for a molecular equation, I'd be done. What if they ask for an ionic equation? All I got to do is scan across the molecular equation that I've just built. Oh, well, I should see if this is balanced or not before I go on, right? It is. Check it out yourself and you'll see that it's balanced just fine. For example, if you look at how many carbons are on this side, there's 2 here and 1 here. That's 3 carbons. There better be 3 over here. There's 1 there and there's 2 there. This is balanced just the way it is. So if I go on and write the ionic equation, all I got to do is scan across this and see if I see any strong electrolytes. And if I do, break them up in ions. How about this one? Is this one a strong electrolyte or not? Well, it looks like an acid, but it is not on your strong acid list. So you look at your strong acid list here, and acetic acid is not on that list, and that means it's a weak electrolyte, and that means that you're going to have to just bring it down just the way it is. So you can't break it up into ions in the ionic equation. How about this one? It's an ionic compound, and it's soluble because it has sodium in it. So you can break that one up. And you break it up like this. Now, usually when you break up an ionic compound in the ionic equation, don't keep breaking it up. You may know that you can strip off a hydrogen ion and have a carbonate ion left behind here. But don't break it up any further than this. When you break it up, try to just break it up so that you have a positive ion and some negative ions. And that's it. Don't keep on breaking it down. And somebody who doesn't know their polyatomic ions might be tempted to say, Okay, well this is H plus C minus, or plus 4 plus 3O minus 2, or something like that. They might say something like that, and that's not right. You've got to leave the polyatomic ions alone. Don't break them down any farther than that. Okay, how about this? Do I break this up? It has to be a strong electrolyte or I can't break it up. Looks like an acid because it starts with an H, but it's not on my strong acid list. So I have to carry it down just the way it is. How about this? Do I break this one up? No, it's not an ionic equation, and it's not a strong acid. It's not an ionic compound, and it's not a strong acid either. So it's a molecular compound. Molecular compounds, all nonmetals, you can just bring down, unless they're strong acids. How about this one? Can I break this one up? If you said yes, you're right, because you have an ionic compound, metal and nonmetal, and it's soluble. So you can break that one up. So there's your ionic equation. Now, what about the net ionic equation? All right, we're going to look for spectator ions, that is, things that are the same on both sides of the equation. They don't really participate in the reaction. And if I look at this, there's only one spectator ion. It's the sodium. It's the same on both sides. Everything else is participating in the reaction. So I'm going to write the reaction down again without the sodium ion. And then this is going to be the net ionic equation. All right, so that's another example of writing down equations for a reaction between two ionic entities in solution. Now, let me do one more quick example. Suppose I give you this reaction. Alright, that looks like a perfectly fine reaction, and it's balanced. This would be the molecular equation. And then I ask you, write the ionic equation. Alright, everything in here, it's going to turn out, is a strong electrolyte. So if I write this as an ionic equation, it'll look like this. That's the ionic equation. How about the net ionic equation? Now, everything here is a spectator ion. So everything here is the same on both sides. And that means nothing happens. There is really no reaction that occurs here. And by writing the net ionic equation and seeing that everything was a spectator ion, I can predict whether a reaction occurs or not. It's asking you to do this in the last couple of problems on the worksheet. Now you should be able to do the worksheet at this point.